morning, students. In the last class we had seen what is an exponential function. Today we are going to study the inverse of an exponential function, which is called the logarithmic function. Logarithmic function, which in short is called the log function. So to study the log function, we'll go back to the exponential function. So we had defined the exponential function as y is equal to b to the power x, where b is a real number greater than 1, and we mentioned that the domain of this function is the set of all real numbers, and the range of this function is the interval 0 to infinity, which can also be written as this, which basically means positive real numbers. So if we draw the graph of this function, we had seen that the graph was a curve, increasing curve, passing through a point on the y-axis whose coordinates are 0, 1. So the graph was somewhat like this. Okay, so here, looking at the graph, you can very easily make out that this is graph of a 1, 1 onto function. So how do we check on that it is a 1, 1 function? We see that for every x there is exactly one value of y. Let's check from here. If we are looking at this value of x, the corresponding value of y is this. If we are looking at this value of x, the corresponding value of y is this. For this x, corresponding value of y is this. So different x's have different images. In other words, different values of y or different images, right? So that means the function is a 1, 1 function. How do we check that it is an onto function? So for onto function, we know we look at the range. The range is from 0 to infinity. You pick up any value of y on the axis, there will be a corresponding value of y on the x-axis. So if this happens, that means the function is onto. And this we have seen in one of the earlier classes also, that if a function is 1, 1 and onto, then the function is invertible. So we get to know here that the exponential function is invertible function. And it is an invertible function. That basically means that the function is 1, 1 onto function. Function is invertible. That also means to say that the exponential function has an inverse, and that inverse is the log function. So how do we correlate? Okay, so before that correlation, let me give you some very simple examples. Like we know that 2 cube will be equal to 8. This is an exponential equation. You have an exponent on the left hand side. So this is an exponential equation. And this equation can be written in the form of log. That means, see, when you multiply basically 2 with itself 3 times, you are able to get 8. Suppose we have a number 8. So what exactly should we do with number 8? To get back number 3. So what should be done to 8 to get back 3? What we are doing to it is some kind of a function. That function is known as the log function. So we can write it down as the same exponential equation can also be written as this. You read it as log of 8 to the base 2 is 3. Log of 8 to the base 2 is 8. So you can see it 2 into 2 into 2 is 8. The same equation can be written as log of 8 to the base 2 is 3. Likewise, now for exponential function we have mentioned that the base has to be greater than 1. So suppose we are taking 3. 3 square is 9. So we can also write down here log of 9 to the base 3 is 2. That means some operation is done on 9 to get 2. What is that operation called? That operation is called the log function to the base 3. Alright, so this is the correlation. So the exponential function here, which we have written as y is equal to b to the power x, I'll just rewrite it as x is equal to b to the power y. So when I'm rewriting like this, does not mean that values of x and y have interchanged. This means that now y is the domain, which is the set of real numbers. What is x? X is the range here. So I'll just write down that the function, this is the exponential function, this is defined from its domain, and the domain is set of real numbers, to its range, which is this 0 to infinity, right? Now let us write down this using the log function. So we can write down log of x to the base b is y. So the exponential function is written like this. So the idea was that I wanted to write down log x. That is why I changed the variables here. Alright, so there should be no confusions about this. So the moment we have written this, now here what is x? X is exactly what is 0 to infinity. Now because I said this is the inverse function, we know that if a function is defined from a to b, then its inverse function is defined from b to a. Alright, so likewise if this is the domain and the range of the exponential function, then for the log function, the domain is this 0 to infinity and the range is the set of real numbers. Alright, so this is one basic concept of invertible functions, which we have discussed in one of the earlier videos also. So this is what we have to remember. So as you can see here, x is the domain. So what is the domain? 0 to infinity. That means the base cannot be 0. The base has to be positive real number. Alright, so now the value of x actually. When we were discussing the exponential function, we mentioned that the base has to be greater than 1. We had seen various cases when base was 0 or 1 or between 0 and 1 or even less than 0. In all such cases, the exponential function was giving out, say, a different kind of a graph. So here, the same concept applies here. When we are using a log function, the base again has to be greater than 1 for similar reasons. Okay, now let's draw the graph of the log function. So here, the log function is log x to the base b is y. So when we assign here different values to x and y, now here since we are not familiar with values of x and y, so we can't put log x value, say 2, log 2, we don't know what is the value of log 2. Alright, so we'll go back to the exponential function, this function, assign different values to x and y and see that the values are, and then plot them. So here we will notice that there is a point, say 1, 0, which is of great importance because when we draw the graph of this function, the graph is somewhat like this. And as you move down the y-axis, this curve will get closer and closer to the y-axis, but will never touch the y-axis. So this kind of a graph is obtained. This is graph of the log function x. Say I've drawn it to the base b. Here, you notice many important things here. First of all, the graph, the point 1, 0 will lie on the curve. That means whenever we draw a graph of any log function, it will always pass through the point 1, 0. Secondly, we notice that the domain of the function is Domain means values of x. So what are the values of x? The graph lies in the first and fourth quadrant. In the first and fourth quadrant, we have values of x ranging from 0 to infinity. X cannot be 0, so that means the domain is 0 to infinity. The range of the function means values of y. Once again, because the curve lies in first and fourth quadrant, in this quadrant, what are the values of y? Right from minus infinity to positive infinity. Now here the graph is drawn like this. It seems to have stopped somewhere here, but the moment we change bases, the graphs will be different. There can be a graph like this also. This way, alright. So like this, the nature of the graph will be the same. So the range in that case would be the set of all real numbers. Now again, starting from the extreme left, say from here, you notice that when you start moving, you are moving upwards. The moment you move upwards, that means this is graph of an increasing function. Increasing function means as x is increasing, the value of y is also increasing. So curve is that of an increasing function. Then the last thing that you notice here is that as you come for values of x which are closer and closer to 0, as you come closer to 0, as x tends to 0, you come closer to 0, this curve will also tend to touch the y-axis. The curve also tends to touch y-axis. Actually, x is not 0, the curve will not touch the y-axis. Alright, it looks like, but it will not touch. Fine. So these are basically the properties of the log function. So once again, writing down the log function, log x to the base b is y, base. Let us look at the base. There can be two kinds of base. Base can be any real number. I am considering two such cases if the base is 10. In that case, you write down something like log x to the base 10 is y. In this case, the log is said to be common log function. Okay, for example, you know 10 square is 100. Alright, so you can write down here log of 100 to the base 10 is 2. So this is that base 10 here which I am referring to. Likewise, the base can be e. This we have seen is an irrational number, almost close to 2.7. So if the base is e, we write down log x to the base e. Fine. If it is base e, we usually do not write down the base. We simply write down log x. So the moment we see log x, it is understood the base is e. In some books, you will also see written log nx. So whenever you come across the words ln, that means the base is e. In such case, the log function is said to be the natural log function. So these are the three ways in which we can write it down. Here again, one important thing we have to notice, that e to the power 1 is e. This is an exponential equation. If we want to write it down in the log function, then we know log of e to the base e is 1. This is again an important result, which in very simple terms can be written as log e is 1. Okay, so we have also seen that it is only the exponential function whose derivative is the same function itself. That is why the exponential function and hence the log function, the natural log function with base e is of say utter importance in calculus or in differentiation. Hence we will study what is the derivative of log x. So here I am directly writing down the result, derivative of log x to the base e is 1 upon x. Now here this is a standard log function. In case you write down the function as say log 2x, then it becomes a composite function, and when you differentiate it with respect to x, so you know you will first differentiate the log function, which gives you 1 upon 2x. This thing goes in the denominator, right? Then you differentiate 2x and you get 2 and multiply by 2. So finally 2 gets cancelled and you get x. Alright, so identify that it's a standard log function or it is a composite log function, and accordingly use a differentiation. Now whenever you are differentiating a log function, what is it that you have to keep in mind? It has to be a natural log function. If it is not a natural log function, that means the base is not e, differentiation is not possible. When is differentiation possible? You want to differentiate, say, log x to the base 10, right? So that means the base 10 has to be converted to base e. So now we'll study some basic properties of log function. So some properties of log function. The first property, I'm right now taking base b, alright. Log of p and q are real numbers, fine. So log of pq to the base b can be written as log p to the base p plus log q to the base b. Okay, the base does not change. Here you are multiplying, which converts here to addition of two log terms. Likewise, if you are dividing p by q and you're finding out log of this quotient to the base b, then it is log p to the base b minus log q to the base b. Log of a to the power n. Base is b. I'm writing b just to denote any base. It can be base e, e as well. So this can be written as n log a to the base b. Now we come to a very important result. If the base of some log function is b and we want to change it to some other base, say c. Alright, so how is that conversion possible? Log a to the base c upon log b to the base c. So you can see here a is in the numerator, this base is here in the denominator, and you wanted to change base b to base c. So this is the formula that helps us to convert the base of the log function. So now suppose we want to differentiate log x to the base 10, right? So first this base 10 has to be converted to base e. So going by this formula, we can write it down as log x to the base e upon log 10 to the base e. Now as I mentioned earlier also, whenever we are writing base e, we usually do not write e. So we can simply write down it as log x upon log 10. And now when you differentiate this, log 10 is a constant. Alright, so that means your differential 1 upon log 10 is a constant. So you differentiate log x and the derivative of log x is 1 upon x. So this is how we differentiate it. So this derivative will not be 1 by x, it will be 1 upon log 10 into 1 by x. So we have changed the base 10 to base e first for differentiation. Okay, now let us also see here 10 to the power 1 is 10. So log of 10 to the base 10 is 1. So this result should not be confused with this. Alright, this is log 10 to the base e. But if it is log 10 to the base 10, then the result can be replaced by 1. Okay, so the bases have to be always kept in mind.